All right, so today we're going to talk about just the idea of a periodic function, and then we'll deal with some right triangle trigonometry. All right, so here's the definition of a periodic function. All right, a function f is periodic when there exists a positive real number c such that f of t plus c is equal to f of t. All right, for all t in the domain of f. All right, the least number c, for which f is periodic, is called the period of f. All right, basically, a periodic function, all right, is a function that repeats, all right, over and over. All right, all trigonometric functions are periodic. All right, some of them have different periods, of course, which is the amount of time that it requires before they start repeating. And we'll get into those a little bit today and kind of more as we go on, especially when we talk about graphs of trigonometric functions. We'll see those. We'll get into that a lot more detail then. Okay, so sine and cosine functions are periodic, and they have a period of 2 pi, all right, which obviously makes sense because 2 pi is one full trip around the unit circle, all right, or one full revolution around any circle, all right. All right, we're going to talk about even and odd uh, functions here. I don't need this by any stretch of the imagination. Okay, so if you remember from way earlier in the year, all right, unit 1 or 2, we talked about even and odd functions. Okay, so just a kind of brief review of what these are. All right, an even function, all right, is symmetric about the y-axis. All right, and when you plug negative x into the function, it doesn't change the function at all. All right. Odd functions, all right, are symmetric about the origin and when you plug in negative x, it gives you the complete opposite of your original function. Okay, so let's look at a couple of examples and see which ones can be odd and which ones can be even. All right, so you'll definitely want a unit circle in front of you. As I said yesterday, pretty much for the next foreseeable future, you will always want a unit circle in front of you. All right, so let's go ahead and just try a few function values, which remember we did yesterday that come straight from the unit circle. So let's look at sine of pi over 6. All right, so remember to do that, all you have to do is go to pi over 6 on your unit circle. Sine is the y coordinate. If you do that, you see that sine of pi over 6 is 1/2. Okay, so now let's try to plug in the opposite and see what happens. All right, so now let's talk about sine of negative pi over 6. Okay, now we talked about, the idea of a negative angle for the past couple of days, all right, on the unit circle, all right. Remember, in standard form, our initial axis is always the positive x-axis, so we always start from here. Positive goes this way, and negative goes this way. All right, so positive pi over 6 is up here. So negative pi over 6 would be down here. All right, and if you look at a unit circle, negative pi over 6 is really the same thing as 11 pi over 6. All right, you can also get that simply by finding a coterminal angle. All right, so if you take negative pi over 6, remember for radian measure, to find a coterminal angle, you just add 2 pi. Well, we would have to get a common denominator here. All right, and we would get 11 pi over 6 that way as well. Okay, so either way that you want to think about it, all right, whether you think about it visually, like graphically, or whether you want to think of it algebraically, which is just coterminal angles, all right, either way is perfectly fine. All right, but anyway, we look at our unit circle. We look at 11 pi over 6. All right, and when we do that, we see that this value is negative 1/2. All right, well, remember, if it's an even function, when I plug in the negative, I should get the exact same. It shouldn't change at all. All right, when it's an odd function and I plug in the negative value, I should get the exact opposite. Did I get the exact same or the exact opposite? Opposite, right? Negative and positive are opposites. Okay, so odd function, we know we can say now that sine is an odd function. All right, and also we talked about reciprocal functions yesterday, right? Cosecant, secant, cotangent. All right. Well, whenever one is odd, its reciprocal is as well. All right. So cosecant will also be odd. Okay. Now let's go ahead. Keep this. Let's go ahead and check cosine now. All right. So let's do cosine, and we can pick any value we want. Let's just do pi over 3 just for something different. All right, so now you look at your unit circle. You go to pi over 3, which is the same as 60 degrees. Cosine is our x coordinate there. All right, so that equals 1/2. All right, well, now let's test throwing in the negative x. Okay, so we'll look at cosine of negative pi over 3. All right, again, you can either think of it as just going in the opposite direction pi over 3, or you can find the coterminal angle by adding 2 pi. Either way, we would see that this is the same thing as cosine of 5 pi over 3. So if we go to 5 pi over 3 on the unit circle, look at the x-coordinate, we get 1/2. All right, did we get the exact same or the exact opposite? The same. All right, so cosine is an even function. All right, and last but not least, let's check tangent. Whoops. And we'll just do tangent of pi over 2. All right, remember to find tangent from the unit circle, we take the y-coordinate divided by the x-coordinate. All right, we also, when I went over the unit circle yesterday, I went around and wrote all of the tangents around the unit circle as well. So if you did that, then you would just kind of have the tangents in front of you anyway. All right, but if we look at, sorry, I don't want to do pi over 4. Let's do pi over, I'm sorry, I don't want to do pi over 2. I want to do pi over 4. It'll be easier for us to do mentally. All right, so we go to pi over 4. Our coordinates there are square root of 2 over 2, square root of 2 over 2. So you take the y-coordinate divided by the x-coordinate. Well, since they're both the same, what is anything divided by itself? 1. Yeah. All right, so the tangent of pi over 4 is 1. So now let's do our even and odd check, right? Let's throw in the opposite of that. So let's throw in negative pi over 4. Again, you can either go in the negative direction pi over 4, or you can find your coterminal angle by adding 2 pi. Either way, you're going to get that this is the same thing as 7 pi over 4. All right, so if we do the tangent of 7 pi over 4, all right, our coordinates there are square root of 2 over 2, negative square root of 2 over 2. So if we do the y-coordinate divided by the x-coordinate, what is the negative of something divided by the positive of the same thing? Like what's negative 4 divided by 4? Or negative 8 divided by 8? Not a trick question. Negative 1. Yeah, crazy. I know. Hard stuff. Hard stuff. All right. So did we get the exact same value or the exact opposite value? Opposite. So tangent and its reciprocal buddy cotangent, all right, will be odd functions as well. Okay. So that covers all 6 of our trigonometric functions. Oh, and cosine's buddy secant, of course. All right. So cosine and secant are even functions. Sine, tangent, cosecant, cotangent are all odd functions. Good times? Good times had by somebody, somewhere. Okay. All right, so here we're just going to do, this is a little bit more piggybacking off of what we did yesterday before we jump into what we kind of just talked about with even and odd functions. All right. So if we want to find the sine of 13 pi over 6, is 13 pi over 6 on my unit circle? No. What does my circle go from in radians? From what to what? Zero. I know, guys, this is like really, really hard stuff, all right? We start at 0. We go all the way around until we get back to what? What's a coterminal angle with 0?
2 pi.
Thank you. Yes, 2 pi. Somebody's paying attention. All right. However, 13 divided by 6 is larger than 2. Do we agree? Yes. Okay. So this is not on my unit circle. All right. However, I can simply find a coterminal angle. So I'm going to subtract 2 pi. Of course, I need a common denominator. Do we all agree that 12 over 6 is 2? All right, so I just subtracted 2 pi. All right, so what do I get here? Sine of what? 13 minus 12 is 1. Yes, 1 pi over 6. I know. Super difficult, guys. I'm really trying to kill you this morning. All right, so the sine of 13 pi over 6 is the same as the sine of pi over 6. All right, so, and that's kind of the idea of a periodic function, right? It keeps repeating itself over and over. So if we want to find something that's not on my unit circle, all we have to do is find that equivalent, that coterminal angle that is on the unit circle. Okay, so sine of pi over 6, we get a pi over 6 on our unit circle. We look at our y coordinate. What do we get? One half. Thank you. All right, very good. Okay, so now we have cosine of negative 7 pi over 2. Is negative 7 pi over 2 on my unit circle? Are any negative angles on my unit circle? No. All right, so I'm going to start here and I'm going to add 2 pi, which is 4 pi over 2. Do we all agree that 4 over 2 is 2? Sweet. All right, we're getting there, people. We're going to think mathematically this morning eventually. All right, so if we do this, all right, negative 7 plus 4 is what? Yep, I know, it's crazy. It is indeed negative 3. All right, now that's still negative. So is that on my unit circle? No, because there's no negative angles on my unit circle. Only values between 0 and 2 pi. So I have to add 2 pi again, which again with a common denominator is 4 pi over 2. Negative 3 plus 4 is, I know, 1. Yes, I know, crazy. So 1 pi over 2. Is pi over 2 on my unit circle? Yes, it is. Crazy, right? It's the same as 90 degrees right up there at the top. All right, cosine is my x coordinate. So what is my x coordinate there at pi over 2? 0. Yeah. All right, now you guys go ahead and try these next two. You're going to have to use, you know, coterminal angles to get to something that is on the unit circle. Take a minute and try to figure out those values. Okay, so let's take a look at these things. All right, so 9 pi over 2, obviously too big. 9 over 2 is larger than 2. All right, our unit circle goes from 0 to 2 pi. So I'm going to be subtracting 2 pi. All right, so if I subtract 2 pi, I'm subtracting 4 pi over 2 with a common denominator. All right, so that's going to be cosine of 5 pi over 2. Again, still too big, so I'm going to have to subtract 2 pi again with a common denominator, of course. All right, so then I get cosine of pi over 2. Oh, hey, that's what we just did up here. So we should know that that is equal to 0. All right, negative 22 pi over 3, really large, like negative-wise. Okay, so we're going to be adding 2 pi, of course, with a common denominator, 6 pi over 3. So if I add 6 pi over 3, all right, I'm going to get negative 16 pi over 3. Still not big enough. So add 6 pi over 3. Negative 10 pi over 3. Still it's still negative, so not on our unit circle. Add 6 pi over 3. We get negative 4 pi over 3. Still negative. Do it again. And we finally get to 2 pi over 3. So, okay, we know that this is really the same as the sine of 2 pi over 3. So we get a 2 pi over 3 on our unit circle. Sine is my y coordinate. What do I get? Well, you guys are going to do miserable on everything this unit, and the next unit, and the next unit, and the next unit, since all of it requires extensive unit circle knowledge.
Square root of 3 over 2.
Square root of 3 over 2. Go to 2 pi over 3 and look at the y coordinate. You said the x coordinate, that would be cosine. All right, so square root of 3 over 2, very good. All right, and that's it. We're done. Okay, so now we're going to use the idea that we just talked about even and odd functions. All right, so if we know that the sine of some angle t is equal to 4/5, all right, then what would the sine of negative t be equal to? Is sine an even or odd function? Odd. So what happens? Will we get the exact same value or the opposite value? The opposite value. So this would just be negative 4/5. That's it. It's that simple. All right. If tangent of t is equal to 2/3, then tangent of negative t would be equal to what? Is tangent even or odd? Odd. So are we going to get the exact same or the exact opposite? Opposite. So this would just be negative 2/3. All right. What about if cosine of theta is equal to 5/7, then cosine of negative theta would be equal to what? 5/7. Why? Because it's even. Since cosine is an even function, when I plug in this negative angle, it doesn't change it at all. It keeps it the same. All right, so that's how we can apply even and odd properties. Okay, so now let's use a calculator to evaluate some trigonometric functions. All right, so we can pull out our handy dandy calculator here. All right, now we do have to be very careful, okay? Just like we talked about how angles can be in degree or radian, All right, our calculator can look at degree or radian. See down here under mode, where you can kind of bounce back and forth between degree and radian mode. All right, that's very, very important. All right, a lot of students miss a lot of problems just because they don't realize that they're doing something in the wrong mode. All right, so if you're dealing with degrees, you obviously want to be in degree mode. If you're dealing with radians, all right, you definitely want to be in radian mode. All right, obviously, since these are in terms of pi, and even more obviously, since they don't have little degree symbols, all right, we want to be in radian mode. All right, so now we can hit sine, and we can do 2 pi over 3. Now, of course, we shouldn't really need a calculator for this since it's a value that's right on my unit circle, right? This would be the square root of 3 over 2. Oh, I think I'm in scientific mode. Yep. All right, so 0.866. All right, which is the square root of 3 over 2 in a decimal approximation. All right.
Where's pi on the calculator?
Pi, if you hit second in this little up arrow, this caret, if you see that blue pi right above there.
Thank you.
Yep. All right, so if we want to do cosine, all right, we can say, all right, well, cosine. And again, we can do 5. Bring up our pi over 7. This we would need a calculator for because 5 pi over 7 is not a value on my unit circle. All right, so this would be negative 0.623. All right, now, we do not have cotangent or cosecant buttons on the calculator. Okay, now, we know that cotangent of theta is equal to 1 over tangent of theta. Okay, so my theta here is simply 1.5. So if I want to find cotangent of 1.5, all I have to do is say 1 over tangent of 1.5. All right, so we can do that with our calculator and say, okay, 1 over the tangent of 1.5, boom, 0.071 if you round it to 3 decimal places. All right, similarly here, we know that cosecant of theta is equal to 1 over sine of theta. All right, so if we want to do cosecant of 2, we simply say 1 over sine of 2. 1.0, actually it'd be 1.100 if you round it to 3 decimal places. Are we okay with just plugging those into a calculator basically? Yes, no, maybe so? Okay. Okay, so now we'll get to a little bit of review of basic right-angled trig, which you should have done in geometry. All right, so if we have some angle theta, we have to have a right triangle. It's very important that it is a right triangle. All right, either of the acute angles can be called theta. All right, now, as we should all remember, the side that is across from the 90-degree angle is called the what? Maybe the hypotenuse? Yes, no, maybe so. All right. Now, what would this angle, this side across from my angle that I'm referring to be called? You guys don't remember anything from geometry. This is the opposite side because it is opposite of my angle that I am referencing. All right, who remembers what the side directly next to this angle would be called? Adjacent. Yay, somebody got one. I'm so proud. All right, adjacent literally means right next to. All right, so it's right next to the angle. Now, do be careful, right? Depending on which angle they talk about, adjacent and opposite can flip around, right? If I was talking about this angle up here, then this would be the opposite and this would be the adjacent, okay? So keep in mind that it completely depends upon which angle you're talking about. Right? The hypotenuse will never change. The hypotenuse is always across from the right angle. Okay, so find the exact values of these 6 trigonometric functions of theta. All right, so in order to do this, we need to know, first of all, we need to know, well, let's get back here before we jump ahead of ourselves. All right, hopefully we all remember SOHCAHTOA. Yes, no, maybe so. I mean, you at least remember having heard it, right? You may not remember what it means, but you remember having heard it. Okay. All right. So what this means, the first 3, okay, sine of my angle theta is equal to the opposite over the hypotenuse. Sine opposite hypotenuse. SOH. SOH. All right. The CA is telling us that cosine of theta is equal to adjacent over hypotenuse. And the TOA is telling us that tangent is equal to opposite over adjacent. All right, now, this is all you would have talked about in geometry, unless you had me for honors geometry, which I think I only have one student. She was an 8A class that had me for honors geometry. Oh, yes, yeah, okay. Yeah, that's 2 years ago, right? Yeah. Okay, so there's I very rarely teach honors geometry, but when I do, I always go a little bit further than most honors geometry teachers do because I always teach honors precalculus, and I want you to know a little bit more for honors precal. All right, so I kind of went into the reciprocal functions, all right, which I talked a little bit about yesterday. All right, so sine reciprocal is cosecant. All right, well, if you're the reciprocal, all you have to do is flip these things, right? So you would be hypotenuse divided by opposite. The reciprocal of cosine is secant. All right, and of course we just flip. So that would be hypotenuse over adjacent. And the reciprocal of tangent is cotangent. All right, so of course we just flip these. adjacent over opposite. Now, I never really think of these functions like this, right, as far as in terms of opposite, adjacent, and hypotenuse. Right? I just find these three and then I just flip them, right, with the actual numbers. I don't really care about all of this stuff. So, okay, so now with that in mind, let's find the exact values of these 6 trigonometric functions of theta. All right, well, first we have to find our missing side. Who knows how we can do that? This is like the one thing you should always remember from geometry.
A squared plus B squared equals C squared.
Thank you, sweet Jesus, that somebody remembered that. All right. Leg squared plus leg squared equals hypotenuse squared, which is A squared plus B squared equals C squared. Okay, now, do be careful. Every year, I have multiple students, right? If you're given the hypotenuse is always C. All right. I've had, I've given kids this, and they still try to say this squared plus this squared equals this squared. No. All right. The leg squared plus the leg squared always has to equal the hypotenuse squared. All right. So in this case, we have 3 squared plus 4 squared equals C squared. That's 16 plus 9, so that's 25. So obviously you take the square root, and this has to be 5. Now, have any of you ever been taught or discussed Pythagorean triples? All right. Pythagorean triples, all right, are right triangles whose sides are all integers. 3, 4, 5 is a Pythagorean triple. 5, 12, 13 is another very famous one. I think it's 7, 20, 21, something like that. There's a bunch of them, all right? And they get there's infinite of them, of course. But, and then any multiples of them would work also, right? So like 6, 8, 10, that kind of stuff. All right, so if you know Pythagorean triples, and you can just, like, it's super easy, like Google Pythagorean triples. Here, I mean, since you're all watching my screen, right? Super easy. Boom. Hey, what do you know? Pythagorean triples. All right, 3, 4, 5, 5, 12, 13. Right, all of these. Right, 7, 24, 25. So I was off on that one. Right, 20, 21, 29. 8, 15, 17. Okay, these are all nice Pythagorean triples where, you have nice right triangles with integer coefficients. I mean, integer sides. All right, but anyway, it saves you a lot of math if you know some of those. Really, 3, 4, 5, and 5, 12, 13 are the only ones that I really expect people to remember. But anyway, so now we can easily do this. Now, do be mindful. This is my theta. All right, so what is this over here in terms of opposite, adjacent, hypotenuse? Yes, this is opposite because it's across from my angle. What is this one? Adjacent because it's right next to it. And what is this one, obviously? The hypotenuse. Okay, so if I want to do sine of theta, all right, sine is opposite over hypotenuse. So 4/5. Well, once I know sine is 4/5, cosecant is very easy. What is cosecant? Hint, it's just the reciprocal. 5/4. I know. Guys, reciprocals are really hard. I know. It's tough stuff here. It's tough. All right, so cosine of theta, all right, we know is adjacent over hypotenuse. So 3/5. Secant is the reciprocal of cosine, so what is it? 5/3. Hey, look out. I'm proud. Proud of you. Doing good work over there. All right, tangent of theta. We know tangent is opposite over adjacent, so that's 4/3. So its reciprocal, cotangent, has to be... That's my girl over there. Only one wanting to answer. I should give you some bonus points or something. All right, so everybody okay with getting the 6 trigonometric functions, all right, from a right triangle? Okay. All right, try this one. Okay, so let's take a look here. All right, Do be mindful, of course, that they give you the hypotenuse. So it doesn't matter whether you call this A or B, but just for convenience sake, I'll call it B. All right, so I'm sorry, I'll call it A rather. All right, so we have A squared plus 2 squared is equal to 4 squared. So A squared is equal to 16 minus 4 is 12. All right, so A is equal to the square root of 12. I'm going to guess the vast majority of you did not simplify this as you should. All right, this is really 2 square roots of 3. Do we remember how to simplify radicals? No. Okay, so let's kind of talk about that. In order to simplify a radical, for instance, if we have the square root of 12, a radical can simplify, all right, and for this case, we'll just only keep it to square roots since that's primarily what we deal with, all right? If there is a perfect square that goes evenly into 12, all right, well, what are our perfect squares? 2 squared is 4, 3 squared is 9, 4 squared is 16, so on and so forth. All right, well, 4 obviously goes into 12, yes? Do we agree? So I can actually rewrite this as the square root of 4 times 3. We do agree that 4 times 3 is 12, yes? All right, well, with multiplication and division, do be mindful, only with multiplication and division. This is not true with addition and subtraction. All right, but with multiplication and division, we can actually break these apart as the square root of 4 times the square root of 3. Well, what is the square root of 4? I know, guys, I'm killing you with tough questions today. 2. So 2 square roots of 3. That's how I got 2 square roots of 3 over here. Does that make sense? Do we remember that from Algebra 1? And Algebra 2, I'm sure, but definitely Algebra 1. In fact, I was tutoring an Algebra 1 student yesterday doing that stuff. Okay, so that's kind of a little bit extra. Just a little side note in case we forgot how to do that, right? Okay, so going back up here, all right, so we now know that this is 2 square roots of 3. All right, now do be mindful, our angle is over here this time. So 2 is my opposite, 2 square roots of 3 is my adjacent, and 4 is my hypotenuse. All right, so we can say, all right, well, sine of theta is opposite over hypotenuse. So 2/4, which reduces to 1/2. All right, which means cosecant of theta is equal to what? 2. All right, cosine of theta is equal to adjacent over hypotenuse. So, of course, the 2 over 4 simplifies again. So this is the square root of 3 over 2, all right, which means secant is going to be what? Yeah, it starts as 2 over the square root of 3. We will have to rationalize this. So multiply top and bottom by the square root on bottom, and you get 2 square roots of 3 over 3. All right, tangent of theta. All right, we're going to get opposite over adjacent. So 2 over 2 square roots of 3. All right, this will simplify. Of course, those cancel. Do be mindful, when everything up top cancels, you still have to put a 1 up there as a placeholder. All right, so 1 over the square root of 3. which would rationalize to the square root of 3 over 3. All right. What would cotangent be? Say that again. Couldn't hear you. Well, you would have to flip it, right? It's the reciprocal. If you did, and then you'd have to rationalize again. However, if you flip this piece, you don't have to rationalize, right? So what would I get if I flip this? Just the square root of 3. Yeah. You can flip this, right? You would get 3 over the square root of 3, and then you would have to rationalize, and then you would get 3 square roots of 3 over 3, and then those 3's would cancel, right? But if you just flip the pre-rationalized tangent, then you save yourself all of that work. Just FYI. All right. Are we okay with those? Okay. Okay, so now we're going to talk about this stuff. All right. It looks difficult. It's really not. All right. So this is actually called degrees, minutes, and seconds. All right, just like time. All right. We kind of think that 360 degrees, like breaking a circle up into 360 degrees, the degree is a very small piece, yes? So why would you need to break a degree up into smaller pieces? All right. Well, if you have a very, very large circle, right, let's say way back in the 14 or 1500s, all right, and you're trying to sail from Europe to the United States, all right, which of course then wasn't called the United States, right, and you're trying to get from, the coast of England to, maybe you're trying to come to Boston, all right. Of course, they used a tool called a sextant back then, and it did use degree measurements and that kind of stuff. If you were off by a degree, where do you think you would end up? Yeah, the very wrong place, right? Because the Earth is so huge that even breaking it up into 360 degrees isn't really quite enough, right? If you're off by a degree, you might end up in Georgia, or you might end up in Maine, right? Which is very far from where you're trying to go, right? And imagine before cars and nice transportation. If you end up in Georgia, you know how long it's going to take you by foot to get to Boston? A long, long, long time. All right. So, yes. All right. So, they broke degrees up into smaller pieces. All right. They first broke them up into minutes. And just like time, there's 60 minutes in a degree. All right. And then they even broke minutes up into smaller pieces. And they broke those up into seconds. And just like time, there's 60 seconds in a minute. Okay. So how we do this here, our calculator doesn't let us plug it in like this. Okay. So we have to kind of convert this to some decimal, convert this piece to a decimal. All right. Well, we know that 5 is going to be 5. That's perfectly fine. All right. Well, if there's 40 minutes, we just said that there's 60 minutes in a degree, right? So we can write that as a fraction, 40 over 60. All right. And then there's also 60 seconds in a minute. So how many seconds would there be in a degree? How many seconds would there be in an hour? It's the same concept. 60 times 60, right? If there's 60 seconds in a minute and there's 60 minutes in an hour, 60 times 60, which is 3,600. All right, so all you have to do is plug this into your calculator. All right, so we get 5 plus 40 over 60 plus 12 over 3600. 5.67. All right. So this, what we're really looking for here is cosine of 5.67 degrees. So we go to our calculator. We have to be very careful. Now we're talking about degrees. So I need to be in degree mode. All right. So now we can just say, okay, well, cosine of 5.67. Now, honestly, you could also have just said this, right? You could have gone here. You could have just done it all in one fell swoop, like this. You get the same thing. All right, so if you don't want to do like separate, you know what I mean? All right, here, cosecant. Remember we talked earlier about cosecant of theta is just equal to 1 over sine of theta. So here you could say, all right, well, this is really just 1 over sine of, whoops, of 34 plus 30 over 60 plus 36 over 3600. All right, so we plug that into our handy dandy calculator. Whoops, I want to do that. I guess I could. I just got lazy with my fraction commands there and decided to just put it in parentheses. All right, so we do that. 0.567 rounded to 3 decimal places. Good times? Good times. Of course, that one's pretty easy to do in your head anyway. 30 out of 60 is 0.5, 1/2, right? 36 over 3600 is 1/100th, so 0.01. So that's really just 34.51, but whatever, same thing. Okay, so now we're going to talk about some fundamental trigonometric identities. All right, there's going to be 3 different sets of these that we will talk about today. We're going to talk about these a lot more in detail in another unit, our trig equations and identities unit. All right, but the first set, you already know, we've talked about them a lot. All right, they're called the reciprocal identities. I abbreviate identities IDs because I'm lazy. All right, and we already know all of these, right? So sine of theta is equal to 1 over cosecant of theta, and cosecant of theta is equal to 1 over sine of theta. All right, cosine of theta is equal to 1 over secant of theta. So, of course, secant of theta is equal to 1 over cosine of theta. And tangent of theta is equal to 1 over cotangent of theta. So, of course, cotangent of theta is equal to 1 over tangent of theta. Those are our reciprocal identities, which we already know. All right. Then we have our what's called our quotient identities. We only have 2 of these. All right. Tangent of theta is equal to sine of theta divided by cosine of theta. And cotangent of theta, since it's just the reciprocal, is of course cosine of theta over sine of theta. Right, then we also have our Pythagorean identities. We have three of these. All right. The first one is sine squared theta plus cosine squared theta is equal to 1. All right, the next one we have is 1 plus tan squared theta is equal to secant squared theta. And 1 plus cotan squared theta is equal to cosecant squared theta. All right, so those are these are the most commonly used identities. That's why they're called the fundamental identities. We'll learn more in future units, but these ones will be used very frequently throughout all of our trig units. All right. Now it is important to note, all right, that sine squared theta or any trig function squared, all right, what this really means is sine of theta all squared. All right. Why don't they write it like this? Why wouldn't you just write it like that?
That means theta squared.
Exactly. All right, because when it's written like that, that just means that theta is the only thing being squared, not the sine. Okay, very good. All right. In a calculator, this is really annoying to do. All right. You actually have to do like sine, and then it'll open up where you have to put your angle, and then you have to close this out, and then you have to square it. So that's calculator, how to put it into a calculator. Very annoying that they haven't just created a sine squared button yet, but they have not. Questions or concerns? Sweet. All right, we'll have one more example here, and then we'll call it a day. And of course, this video will be up later today, so if you missed something or didn't quite get something down in time, you can always go back and look at it. All right, so let theta be an acute angle such that cosine theta is equal to 0.96. All right, find the values of sine of theta and tangent of theta. All right, so first, we're only given one piece. All right, so we have to find one of these identities, all right, where I only have one missing piece. Okay, I have cosine, so I could find secant, but that's not one of the things they ask me to find. Okay, I have cosine. They ask me to find sine and tangent, but when I have two missing pieces, I can't solve for them, right? You can only solve when you have one missing piece. All right. Here, I have cosine. I'm looking for tangent, and that's my only missing piece. So let's go ahead and use this one first. All right. So I'm going to say sine squared theta plus cosine squared theta is equal to 1. That's what I'm going to use first. Of course, I'm looking for sine. All right, well, cosine theta is 0.96, so cosine squared theta is 0.96 squared. All right, if you do 0.96 squared in the calculator, you get 0.9216. All right, so now I subtract that from both sides. All right, and we will get sine squared of theta is equal to 0.0784, I believe, should work. So then, of course, to get sine, I need to take the square root of both sides. And that is 0.28. And now technically when you take the square root, this could be positive or negative, and depending on which quadrant we were in would depend upon like whether this is positive or negative. All right, but it tells us that it's an acute angle, which means it's between 0 and 90 degrees. And in that first quadrant, everything is positive. Okay. So now we know sine. We need to find tangent. There's a couple of different ways that you could do this. All right. We could use cosine to find secant, and then we could use this. All right. Or we could just go ahead and use this. This is the easiest way. Tangent of theta is equal to sine theta over cosine theta. So I know that tan is equal to sine over cosine. All right, so in this case, it's going to be 0.28 divided by 0.96. All right, which will be 0.292 rounded to 3 decimal places. And we are done. We have found sine and tangent from just being given cosine. And of course, from here, it'd be very easy to find all of the other three, right? You just take the reciprocals. All right, of course, no need to worry about that. Your homework is on Delta Math.